So welcome everyone to our STAMPS webinar series. We're very fortunate to have Dr. Chen here today. Yang is an assistant professor of statistics and the research assistant professor at the Michigan Institute of Data Science, also called MIDAS. Yang received her PhD in statistics from Harvard University. And before that, she studied mathematics and applied mathematics at the University of Science and Technology in China. So Yang's research interests include computational algorithms in statistical inference in the field of biology and astronomy. I know she has recently done some excellent work in predicting solar flare intensity with machine learning models. Today's talk will be in the area of space weather and space science, and the topic of handling missing data in GPS satellite signals. And Yang just told me that you will be the first one that hear this talk. So the topic or the title will be matrix completion methods for the total electron content video reconstruction. So Yang, please take it from here.
Yeah, thank you so much for the introduction and thanks for the invitation. And today I'm going to talk about my recent work in the field of space sciences. Over the past 3 or 4 years, I've been concentrated in applied statistics in the field of astronomy and space sciences. And I was talking to Anne before this talk that I've been presenting my solar flare prediction talks many times before this. So this time I just want to try something new to also get myself refreshed. So this is pretty recent work. We have one paper accepted and another paper in draft. So any suggestions or comments or criticism is welcome. And feel free to ask any questions during the talk. So I'm going to talk about matrix completion methods, or in other words, video completion methods that we developed, especially for the total electron content video reconstruction problem. But the methodology is kind of general, as you could see. This is joint work with my students and colleagues at the University of Michigan and the Department of Statistics and our collaborators from the Climate and Space Science Department. So first of all, I'm going to give some background about what is a total electron content map. Or we call it a TEC map. Before working on this project, I actually had no idea about what this was. I'll talk about what kind of existing methods people use within the field to monitor the TEC maps. And then I'll talk about our proposed methods with some empirical analysis. And if I have time, hopefully, I'll talk about our ongoing work, which is still immature, but quite exciting for us, which is about prediction models for total electron content maps, especially in face of missing data problems too. And I'll conclude with our ongoing and future plans. So what is a total electron content map? There is a special layer in the upper atmosphere around 70 to 1,000 kilometers above the Earth, which is called the ionosphere. And the total electron content map is actually trying to measure the total number of electrons in the path between the satellite radio transmitter and the ground-based receiver in the ionosphere. And the units is in terms of 10 to the 16 electrons per centimeter. So in this picture, I'm just trying to show, this is not my figure, I brought it from somewhere. I'm just trying to show the definition of the total electron content. This is the position of the satellite, the global navigation satellite system. And here is the receiver. And then what we're trying to measure is actually this, how many electrons exist per square meter, how many electrons exist in this kind of cylinder. And typically people care about the so-called vertical total electron content, which is you do a projection towards the vertical direction. And here we just overall just call it total electron contents. And this is the quantity that we're interested in. And the real-time monitoring of the total electron content is quite important. In one aspect, the total electron content affects the propagation of radio waves, leading up to tens of meters positioning error in the GNSS positioning navigation timing services. So better knowledge of this total electron content map will make our services more accurate. So that's why the real-time monitoring is really important. And also sometimes the total electron content measurement has been used in earthquake monitoring, modeling, and prediction. And typically people say a significant reduction in the TEC value is observable for at least 3 days before major earthquakes. So that's why we do want to have very good high resolution real-time monitoring of the TEC maps across the globe. So that's the scientific motivation. And now I'm going to talk about the databases that's available to us and the databases that people have been relying on in order to do this kind of real-time monitoring of the total electron content map. And also the data set will also reveal some of the statistical and scientific challenges in terms of reconstruction those maps. So we have 2 different databases. One is called the Madrigal database. So this kind of databases, as I can show with one example here on my left panel of this plot, it is a global map of vertical TEC measurements, and it has a spatial resolution of 1 latitude by 1 longitude, and a temporal resolution of every 5 minutes. So essentially, you observe those colored dots at a 1 latitude by 1 longitude spatial resolution and time resolution of every 5 minutes. And you can see a lot of patched missingness here and there, especially in the ocean area. Because here you probably could see, here is where we are in North America. Oh, sorry, here is. So that's the land. And then in the ocean, you don't really have a lot of coverage. And sometimes people will use, I would say, a state of art of the field is trying to do some medium filter, which is a 3x3 medium filter, to make sure the missingness is not as bad, but still there are a lot of patched missingness here and there, especially around the ocean area. And even in the land area, there are missingness here and there too. But it is a very high spatial and temporal resolution data set. An alternative data set is called the IGS TEC maps, which I'm showing on the right-hand side of my figure. And this is actually based on spherical harmonics fitted TEC maps based on a more scattered number of locations. So it's the data is kind of the entire map is reconstructed based on a much smaller number of stations, the receiver stations that we have, and the spatial resolution is much lower, it's 2.5 by 5, and the temporal resolution is also much lower, it's every 15 minutes. And of course, people are not super satisfied by the quality of this IGS dataset because it is of low spatial and temporal resolution, and also it's kind of overly smooth by the spherical harmonics fitting, which we'll talk about momentarily. And so that a lot of the mesoscale structures or the smaller scale structures are actually not preserved in these maps. So what we actually want to do is actually to take advantage of this higher resolution observations and trying to reconstruct a TEC video so that we have very high spatial and temporal resolution. So that's just some descriptions about the dataset. Our goal is to fill in the missing values in the Madrigal dataset to create high resolution TEC maps. And the patterns of missingness in the Madrigal TEC maps database are quite interesting to me. That's why I got started working on this project. First of all, we have big patches of missingness in the ocean area. And we also have scattered, but those are not not at all random missingness in the land area. And actually, what's more interesting is that we have temporally moving missingness patches, because what we're observing is actually the part that faces us. And then as the Earth rotates, the patched missingness actually change. So at one particular time frame, we might be able to observe a particular location, but at the next time frame, we may not be able to observe that particular location. So this kind of interesting temporally moving missingness patches feature actually enable us to come up with an algorithm that takes advantage of this kind of missingness pattern so that we can do better imputations. So the existing methods, I will list two of them here. One comes from the field of statistics and the other comes from the field of space sciences. One is to frame this problem as a matrix completion problem. This is a pretty classical technique for completing scattered observed matrix. So it's commonly used in designing recommendation systems, especially in industry. You can infer the potential rating of a user given to if he or she is given an item that he or she has never consumed. So there's a lot of work on this. I'm not going to list all of them. I'm gonna briefly mention one of them, which is called self-impute ALS, alternating least square, proposed by Hasty et al. In 2015. So the framework of this matrix completion with factorization is very straightforward. What you want to do, xt is the filled-in matrix, and this is the Frobenius norm of a factorized matrix. So AT is the first factor, and BT is the second factor. So this is essentially the L2 loss function that we have. And then because it's called soft impute, so we have a L2 penalty here. It's like a ridge regression problem essentially. And then the fitting of this soft impute algorithm is by alternatively updating AT and BT. So if we fix AT as a constant, then as of this loss function essentially is equivalent to the ridge regression because it's for BT is shrinking towards 0, and then you have a L2 loss. And similarly, if we fix the BT, this is essentially a ridge regression problem for AT. So closed form solutions can be derived at every iteration, and we'll just iterate the two different steps until convergence. The algorithm is very fast, and it can give satisfactory performance in a lot of the situations. So let's see what they can do for our TEC maps. So on the left-hand side, I'm showing the original total electron content map, which has scattered missingness here and there in the land area, and a large patched missingness in the ocean areas. And here's what we can achieve with self-impute. When we first saw this result, we saw, well, it's decent. However, it's actually doing something that's a little bit more than what we're asking for. So the undesirable parts include those big blue bands, as you could see, the verticals and the horizontal big blue bands here and there. Those are very artificial structures that we don't expect scientifically. And I think statisticians can easily understand why this is going on, because similar to ridge regression, are shrinking towards 0, and especially in the regions where you have almost no information from the true observations, you will have imputed value being very close to 0 in this scenario. Or in other words, those are created by our algorithm. So this kind of big blue bands, and especially the big blue patch here, are purely non-scientific and not satisfactory from a scientific perspective. Although for some other areas, for example, this bubble area, we're actually pretty satisfied with what it's achieving in terms of imputing the neighboring values of observed values. So we would say the soft impute ALS is good for some regions, but undesirable for some other regions. So that's one of the existing methods. So within the field of space sciences, people have been using this method called spherical harmonics fitting. So it's trying to approximate data on the surface because the total electron content values are around the globe. So we can do some transformation to put them on the surface with a linear combination of several basis functions. So typically, it is set up as follows. Is a summation of the number of terms that you have in the basis function, and then there are some coefficients. And the basis functions are essentially fixed. So it's a least squares problem for the fitting. Still pretty simple, easy to tune, and provide decent results for the field of space science over the past few years. And that's why people have been using it. So the spherical harmonics basis functions will look like this. It looks pretty beautiful. And this is what we can achieve with our total electron content maps with a spherical harmonics fitting. So the original map is here still, and then the fitted map is here. So if you still remember the soft impute ALS results that I showed you just now, this map seems so smooth to us. And that's also not desirable because it could maintain some global structure saying, well, this side is facing the sun, so it should have high values. But other than that, the mesoscale structures or the smaller structures are all smoothed away by this spherical harmonics fitting. And sometimes people will say, well, why don't you just choose a higher order in the spherical harmonics fitting? Well, we did, and the result come out quite funny in a sense that it's still super smooth across the global scale structures, but in some local structures, they will come up with artificial holes here and there just because of the overfitting issue that we faced with when we artificially increase the order of the spherical harmonics fitting. So the lesson that I want to learn from using those two sort of default methods coming from either the field of statistics or the field of space science is that, well, the method could make a mistake on both sides. It might overfit some of the regions, or it might create artificial structures, or it might overly smooth a lot of the global regions. So those are not desirable. And that adds more motivation for us to develop our own methods to impute the total electron content maps. Here just a recap what we can achieve with soft impute and what we can achieve with spherical harmonics fitting. And essentially, finally, we want to come up with somewhere in between. So that comes our proposed method, which we call the VISTA method. So the final framework has the following features. We want to impute a time series of TC maps or TC videos at the same time, instead of matrix by matrix. The previous two methods are all matrix by matrix. We want to use a matrix factorization formulation still, just like the soft impute. And we want to use the spherical harmonics as a warm start, and we call it auxiliary data, because that kind of data can preserve some of the global structures so that for the big patch, the missingness, we can benefit from that. And we want to penalize the matrix norm for the factor matrices, similar to the soft impute. And we want to reinforce the smoothness of the imputed results temporally. And this is based on scientific intuition that for neighboring frames, they should not, the TC values should not be different too much. So finally, our objective function has the following form. We have the imputation loss, which is still the L2 loss for imputation, plus matrix norm penalty, similar to the self-imputed LS, and plus temporal smoothness penalty, plus auxiliary data penalty. Or mathematically, it is framed as follows. And we call it video imputation with self-impute, temporal smoothing, and auxiliary data. The first two terms are very similar to what you have for the self-impute LS. And this term is to reinforce temporal smoothing. So essentially we penalize the difference between the imputed matrix at time t versus time t minus 1. And also we penalize the distance of the imputed matrix AT and BT versus the auxiliary data YT. And we assume the YT, this auxiliary data, has no missing values. So that's our objective function. I just want to remind everyone about what we achieved with the self-impute method and the spherical harmonics fitting map. So what we're trying to do here is that we're trying to borrow information from this very smooth map. It could come from spherical harmonics fitting, or it could come from some other database. At the beginning of my talk, besides the Madrigal database that we're working on right now, we also have the IGS database. So that one could also serve as auxiliary data here. So we're trying to borrow information from auxiliary data. And also we're borrowing the idea from self-impute to frame this imputation problem as a matrix factorization problem. So essentially, finally, we're combining those two results and adding in this temporal smoothing component. So that comes our main algorithm. So how do we implement this? It's actually not too bad. So in total, we have kept the number T of frames to be imputed at the same time. It's a video of TEC maps, and each frame has its own AT and BT factors. As soon as we get those factors, we have the imputed map. And what we want to do is to just update the factors cyclically in a way that we update A1 and A2, keeping all others fixed, and then do it round and round and round. And at each of the steps, when we fix all of the other matrices, for example, where we are trying to update A1, we adopt a majorization minimization algorithm. Because this time, when we take into consideration of all of those penalty terms, it's no longer a super simple, it's no longer a simple ridge regression problems. So after the majorization minimization problems, we just do a list of squares. So still, within the majorization minimization algorithm, we still have a closed form solution from a list of squares fitting, so that we don't really need to do any kind of gradient descent or anything like that. So the final algorithm is pretty straightforward as soon as we get to that point. At the kth iteration, we want to update AT, and then the other factors, the A1 until AT minus 1 has already been updated, and then the B are still at the previous iteration, and then the objective function that we have is a function of AT, which is defined by this QT function. And we can locate where the ATs are and then try to find a solution. The only complication comes from this, this term, because for the loss function term, we only have a loss, we have an explicit loss only in the observed locations of the matrix. So that's why we have a operator P omega T here, which is only taking the observed locations in the in the TC maps. So that's why here we don't really have a full like AT component here. It's taking the non-zero values for the XT component for this particular matrix. So that is why, given this particular situation, we need to do a majorization minimization step in order to solve for the AT. So what we do is we want to upper bound this particular term, which is the L2 loss term, by a simpler function as a function of AT. So the trick that we did is that because omega t is taking the non-missing entries, so omega t orthogonal is the complement, which takes the missing entries. So the L2 norm of this operator should be smaller when you add in an extra term. So this extra term could be anything, but it has to be within the set of omega t orthogonal. That's the complement for omega t. And then after some rearranging, because this p omega t is a linear operator, so after some rearrangement, we can result in this formula. And this term is so much easier for us because looking at it as a function of AT, it is quadratic. So again, we come back with another minimization problem for quadratic function for AT. And we of course know what is the closed form solution for that one. So finally, the AT has a solution that looks as follows. If you come from a Bayesian perspective, you'll recognize that this is essentially a Bayesian shrinkage formula, and the shrinkage factors are determined by a combination of the tuning parameters, lambdas, lambda 1, lambda 2, and lambda 3, which are essentially the coefficients before the different penalty terms, and the BTs. So this shrinkage formulation for the update for AT reveals the fact that the AT and BT are self-regularizing as shrinkage factors. And this is also revealing how much contribution we're having from, for example, the matrix norm penalty, from the temporal smoothness penalty, and also coming from the auxiliary data penalty. And intuitively, from a computational perspective, we can understand this kind of shrinkage formula in a sense of how much we're learning from the temporal smoothness, how much we're learning from the auxiliary data for our imputed maps. So this essentially goes to our final algorithm. I'm not going to go into the details of this. You can find it from our paper. And we do have some theoretical guarantees, which are quite similar to the theoretical guarantees given by the soft-impute ALS methods. First of all, we can show that our objective function is non-increasing. I just want to acknowledge that we didn't really prove any global minimum for our solution to the problem. And what we can show is that across the different iterations in our majorization minimization procedure, our objective function is never increasing. And also we could derive a convergence rate lower bound, which is a function of the number of iterations, and also written explicitly as a function of the tuning parameters. Talking about tuning parameters, there are two different sets of tuning parameters that we need to tune for this particular algorithm. And in here, I also want to highlight the advantage of our particular algorithm. So for the VISTA model fitting, we have tuning parameters which are related to the three different penalty terms: the matrix norm, temporal smoothness, and auxiliary penalty. And what is interesting is that our method is quite robust as long as those three different tuning parameters are within a particular range and is not sensitive at all. as you move across the region that we identify. For example, as long as we set the lambda 1, lambda 2, lambda 3 values to be within those boxes, our performance for the VISTA model does not change much. And in this way, in our real application, we actually just fix those tuning parameters instead of tuning them every time that we have a time sequence of TEC maps. In general, we still recommend cross-validation procedures, but like with a 3-dimensional parameter space, cross-validation could be time-consuming, especially if you don't know where to get started. And in our numerical studies, I can also show, like, even if you don't do a full cross-validation, you can still achieve very good performance as compared to the ground truth. And also, I just want to mention that as compared to competitive methods in the literature, our method actually stand out in terms of non-sensitivity to the tuning parameters. And the other set of tuning parameters that we have is about auxiliary data generating. So in a spherical harmonics fitting procedure, that is the auxiliary data creation, we need to choose the number of basis functions and also the one penalty terms. So we did it by cross-validation. And the way that we did it is by just masking out a proportion of the observed signals, pixels, and then fit on the rest. And in our practice, this cross-validation does not take too long for like for a TEC video of 288 frames. So that's not too bad for us. And now I just want to show some empirical results coming out of our VISTA methods, both from simulation studies and from the imputation of the total electron content maps. So the design of the simulation studies is actually to mimic what is really going on with the real data, especially in terms of the missingness. And the benchmark data that we're using is the IGS database, which I introduced at the beginning of the talk. This is a lower spatial temporal resolution dataset, but it is a full dataset. There's no missingness in this particular dataset. And it's also about TEC values. So we use this as a benchmark in our simulation studies and artificially create missing values according to different patterns that we design and trying to showcase our performance using this particular data set. So each day of the data is of size 181 by 361 by 96. And the missingness patterns that we observe is as follows. So here is the IGS dataset. We have first random missingness. So just across the globe, we create 70%, for example, missing entries. So that leaves us with this kind of observed pattern. And everyone should know this is like a simple case because it's spatially uniformly distributed, simple random missing. And also we can create temporal missingness that is kind of trying to mimic the pattern that temporally there is some consistency in terms of the missing and observed information. And we also create patch missingness. That means there is a certain region in which the entire region is not observed. So this region could be small as what you see in the map, or it could be larger. And we also have temporal patch missingness. That means we have a patch that's missing, but across different time, this patch moves along across this image in a certain pattern. So that's the 4 different kinds of missingness that we consider in this design of the simulation studies. the random missingness, we consider 30, 50, and 70% of the missingness for that. And similarly, temporal missingness, we consider also 30, 50, and 70% missingness. And the missingness mask will move 6 columns horizontally at each time point. And random patch missingness, we create smaller patches, for example, 27 by 27, or we create large patches, which is 63 by 63. For temporal patch missingness, we consider similar patterns of the patches, but we move those boxes at a speed of 6 columns per matrix at each time point. And we do this temporal missingness pattern anti-clockwise, so that will range across the globe in terms of where it is missing. And the methods that we adopt are as follows. The benchmark model is the soft impute LS. And actually, we choose this tuning parameter such that the soft impute LS has the best performance. So this lambda1 is tuned such that based on a cross-validation procedure for soft impute. And for other competitive models that we propose, we stick to this particular parameter. So we don't tune our algorithms anymore, just stick to the use of the lambda1 to be the same value as the soft impute. And then we could set lambda3 to be 0, that is, we only include temporal smoothing. Or we could set lambda2 to be 0, so that we only include auxiliary data smoothing. And finally, that's our full algorithm, the soft impute plus the temporal smoothing plus the auxiliary data. So those tuning parameters are set to give like a suboptimal performance for our finally proposed full model, but we're trying to bring in the best performance for the benchmark models. And the evaluation criterion that we have is called the relative squared error. The reason why we're not using the mean squared error because it's a bit more sensitive to the absolute values of the original map. So the relative squared error is essentially trying to normalize it using the imputed values, using the true values. So here's a comparison of the performance of the three different different methods versus the different missingness pattern. So as we could see, the spherical harmonics actually does pretty bad. That's corresponding to the one, and in the random and temporal missingness patterns, the temporal smoothing is actually helping a lot as the percentage of pixels missing increases from 30% to 70%. And finally, our full model, which is the blue one, the one with the temporal smoothing and also the spherical harmonics rating, is actually doing very well in all cases. And this is the result showing the other two patterns of missingness, the patch missingness, which is here, and the temporal patch missingness, which is here. The one that's mimicking our total electron content maps the best is actually this last scenario, because as I mentioned before, in the ocean areas, we have very large patched missingness, and also because the Earth rotates relative to the sun, then we also have temporally moving missing patches. So in face of that situation, the full model, which is the one with the temporal smoothing and spherical harmonics fitting, has the best performance across all alternatives over the baseline, which is the soft impute LS. So this is just some visualization results based on our simulation data. So here is the ground truth. This is what you get from soft impute. There will still be some artificial structures from temporal smoothing, from spherical harmonics or fitted, and this is our full model. So here is the imputation of the full TC map. We want to showcase our results based on a storm day and a non-storm day. For the data coming from a storm day, it behaves quite differently from the data coming from a non-storm day, especially in terms of how much temporal smoothness that you might need. So our tuning parameters are determined based on a grid search. And we randomly drop 20% of the observed pixels and use them as test set and fit our model with the rest of 80% observed pixels. So here's the bunch of results that we get on a storm day, that's the top panel, and then on a non-storm day, that's the bottom panel. So the first row is the self-imputed LS result. The second row is the temporal smoothing model. The third row is the model with the auxiliary data, and this fourth row is the full data result. And this is the benchmark from the state of art in the space-time field, directly using spherical harmonics fitting. So in terms of test set RSE, of course, our full model is doing the best across the storm day and non-storm day. And we are actually doing a lot better than the state of art for the field of space science in terms of both the RSE and MSE. So here's the result from a non-storm day. The original map looks like this. Auxiliary map from spherical harmonics fitting looks super smooth, and our full model is smooth enough to capture the global behavior, but also good enough to capture some local mesoscale structures. So that's the desired part. And at the contrast, the self-imputed LS method is giving us a lot of those blue bands here and there, which is not desirable. And here's another example, which is on a storm day. So the behavior of a storm day is quite different from the non-storm day. And the Missingness pattern is a little bit different. And again, the spherical harmonics fitting is actually very, very smooth. But in our full model, we can actually do pretty well in terms of detecting this so-called bifurcation behavior, and also detecting some interesting mesoscale structures, which are really important along the equator. So those are very important results that we could obtain scientifically. So I probably have another 10 minutes.
Yeah, about
10
10 minutes.
Yeah, I'll briefly talk about our ongoing work on the prediction model for total electron content maps, because all of the previous results are showcasing how we do the imputation for the videos. So in general, what we want to do is to build a matrix-based autoregressive model for forecasting TC maps hours into the future with the following highlights. So we'll build a VISTA database based on the VISTA method that we just presented just now. And we want to combine data, multimodality data, in the sense that we want to utilize both the past VISTA imputed TC videos and also some other relevant global parameters. Those are vector parameters to jointly predict the TC maps. And the algorithm that we rely on currently is still kind of like iterative least squares method. So now I just want to highlight what are the challenges here in terms of prediction. First, we're trying to predict a video of matrices. So this is a pretty large scale structure. And also some of our predictors are actually time series of vectors. So typically, if you want to go from a higher dimension to a lower dimension in terms of prediction, it's easier. But in our case, we're trying to predict from vectors to matrices. So that adds some more trouble. And especially when we are trying to combine those vectors together with the videos, and especially when they are highly correlated. So that creates more trouble for the prediction models. So the proposed model that we currently have is as follows. Let me just briefly explain. So here is a bunch of autoregressive terms. We have a left matrix A and a right matrix B operating on the latitude and longitude separately on the past values of the TC maps. So this is like a leg P autoregressive term. And then in terms of the vector features, the way that we use it is by specifying matrix basis functions based on the spherical harmonic spaces, and then try to do a linear combination of those vector features, just like a linear regression term, to actually project this lower dimensional matrix to a higher, to project this lower dimensional features to a higher dimensional matrix. And here we also consider leg S for the vectorized features in the prediction. And ET is just the error term, which we assume to be Gaussian after some transformations. And this is motivated from the literature on matrix autoregressive models. And what is unique here is not only multiple leg matrix autoregressive models, but also a clever way of constructing matrix basis functions and then try to adopt ideas from linear regressors to project the vectored features into a higher dimensional matrix framework. So the vectorization operator will actually make the model look even simpler. So after doing the vectorization, we can see essentially the autoregressive coefficient before this this leg P term is the tensor product of the right operator and the left operator for this. And this will enable us to do a lot more theoretical work much easier. So I'll skip this interpretation term and then talk briefly about the estimation algorithm. So essentially, we are still thinking about using a loss function of L2 loss function because we're assuming the noise term to be Gaussian and homogeneous Gaussian in that sense. And still, we want to iteratively update A, B, and the beta factors here. So for each of those steps, they are essentially least squares fitting. So those are not too difficult. We still try to update one of them at a time while fixing all others. And the convergence empirically is actually not too bad. So here I just want to show some of the preliminary results that we get from our prediction model. So we have already used our VISTA method, which is the imputation methods that I introduced to construct a full database of total electron contents in the year 2017. So we have entire VISTA TC maps available at a 5-minute time cadence. And we also have some vectored so-called solar wind parameters available at a 1-minute time cadence. And it would take the first 20 days of August 2017 as the training set, and the other 5 days as the testing set. So essentially we have around 2,000 frames for model training and 500 frames for testing and performance. So here is some of the results. I just want to recall that The P is the number of terms in the autoregressive part, and the S is the number of terms that we use for the solar wind parameters. That's the vectored predictors. As you can see, as we move from autoregressive term being 1 to autoregressive term being 3, the results get better, significantly better across all lead time predictions. We're considering lead time of 15 minutes, 1 hour, and 3 hours. So in the field of ionosphere monitoring, the 3-hour prediction is actually a very, very long prediction window that we are trying to stretch ourselves against. And also that adding some of the solar wind parameter terms sometimes could improve the results. For example, if you compare the autoregressive terms equal to 1, adding solar wind parameters actually improves on top of the baseline model when you don't add solar wind parameters. So that means we do have some success in terms of constructing the basis functions, the basis matrices, and using the solar wind parameters as extra predictors for the prediction model. And what is not as desirable is that as we increase the number of legs for the vectored predictors, that's the solar wind parameters, our performance actually decrease. So that's clearly showing some sign of overfitting and over parameterization in our model. So this is something that we're still working on, both from a theoretical perspective and also from a computational perspective. So that's just a very, very quick view of our current ongoing work on the prediction model. And finally, what we actually want to do is to go from the raw data to the full prediction. Or in other words, we should start from the incomplete observed TC maps and then do a prediction for a complete TC map. And currently what we're doing is actually a 2-step procedure. We're imputing the TC maps, imputing the TC videos first, and then try to do the prediction on top of the imputed maps. So that will be our final step. So here I'll just try to conclude and talk about future directions. We proposed a new imputation method called VISTA to impute total electron contents maps with over 50% of data missing. It creates a low rank structure for the imputation, and the temporal smoothing is trying to borrow information at adjacent timestamps and smooth the low rank structure. Spherical harmonics fitting or the auxiliary data provides a warm start for the imputation, and it works particularly well for the big patches of missingness. And our empirical results show that there are some improvements on both the global scale and mesoscale reconstructions that we have. And our database is gonna be super valuable for the field of space sciences to do real-time monitoring for the TC maps. And in terms of future plan, currently we're trying to release a data product containing the imputed TC maps based on the VISTA for the last solar cycle that ranges from 2009 to 2020. And the database is ready and paper is in draft. And in terms of prediction models, we do want to give uncertainty quantification for the model predictions that we have, which is what the current methods based on deep learning that has been adopted by space scientists, they cannot give. And we do want to derive the joint asymptotic properties of the estimators for the left operator, right operators, and also the regression coefficients for our prediction model. This is ongoing. And we want to provide a complete imputation prediction pipeline for operational use. And again, a third step for us is really to go from raw data to real prediction, going from the incomplete TC maps to the prediction of full TC maps. So I'll try to stop here, and thanks for your attention. And let me know if you have any questions.
Right. Thanks so much for an excellent talk. And we have time for some questions from the audience. Otherwise, I have a bunch of questions.
So I actually have a question. I have no idea where the raise hand button again is. I think it keeps moving
Oh,
around.
it's okay. You can talk.
Can I ask? So in the end, you mentioned uncertainty quantification and you talked about uncertainty quantification for the prediction. But how about uncertainty quantification for the imputation? Like, is that actually something that's possible? Have you thought about that? Then what could be done for the uncertainty of the imputation?
Yeah, I think that's a very good point. We have thought about it, but it is actually something that I don't really know how to convey or how to visualize or how to quantify, because pixel wise, I could theoretically offer uncertainty quantification, because if you look at our loss function, it's essentially a Gaussian Markov structure that we have. And formally can formulate it as a Gaussian distribution for most of the terms, and we could offer. But like in terms of a global map or a video, how would you present your quantified uncertainty is an issue that I've been struggling with. So that's why I did not really report or work towards the uncertainty quantification, especially for the imputation.
Yeah,
Great.
Yeah.
So in spatial statistics, you often have a very similar problem, and I guess the issue that you're pointing out is that if you could maybe provide some point-wise answer on this, but that doesn't really convey the whole picture, because things really are correlated. You want to know how those patterns will kind of depend. So what people do as an alternative would be to provide simulations from like the joint distribution of everything. So provide like in climate they sometimes talk about ensembles. So you provide like an ensemble of simulations from this big model. If there's an underlying model, it wasn't immediately clear to me that there would be an underlying model, but now
it's like a Monte Carlo representation of the uncertainty.
That's correct. Yes.
Yeah, I mean, I'm thinking about there's also random imputations. I don't know if Larry, you worked on that, or Yang Chen. What was I saying?
Yanqi?
Yeah, Yanqi did random imputations, right, for the structures that you were working on. I think so. I heard a talk maybe last year at Texas.
Oh, I don't know. I didn't.
There's a field on random imputations, because he's filling in those structures. I just got a brain blip here. What are they called? You worked with Yanqi on that. The filaments.
Oh, the filaments.
Yeah,
oh,
so he was working on random imputations for that.
I wouldn't call it imputation what he was doing, actually.
Yeah, he had some other term, but mainly was saying that instead of filling in by prediction, where you get the mean, he had a stochastic model for it.
Is it like a multiple imputation?
I think there's probably a word for it, but since I'm not working on it, I can't remember. But it's not.
Yeah, but I think it's a good point that the Monte Carlo representation of the uncertainty might be something that's helpful in practice.
Yeah, that's what we found out in these certain climate applications. And it's also nice because, otherwise you would have to provide some really high dimensional covariance matrix potentially. And actually that will only summarize the second order behavior of the uncertainties. But, even providing that matrix would be typically infeasible with these large maps. But you can provide like some handful, some, reasonable number of those sort of Monte Carlo representations from the distribution. And that's something we've been looking at in certain climate applications. It seems like a good idea in situations like this.